I would like to introduce Professor Linga Reddy. Professor Linga Reddy received his master's degree in electrical engineering from the Indian Institute of Technology, IIT Delhi, India, in 2004, and the PhD degree in electrical engineering from the Norwegian University of Science and Technology, NTNU, uh, Norway, in 2011. He worked for Texas Instruments in mixed signal circuit design before joining PhD program at NTNU. After finishing his PhD, he worked in radiation imaging and for atmosphere space interaction monitor at the University of Bergen, Norway, from 2010 to 2012. At present, he is leading a group on autonomous and cyber physical systems research group at and working as professor at the University of Agder, Norway. He has co-authored over 100 research publications in prestigious conferences and journals. His main scientific interests are in cyber physical systems, autonomous systems, and wireless embedded systems. He is the principal and co-principal investigator for many research grants from Norwegian Research Council. He is a senior member of IEEE. He is also a member of editorial boards of various international journals as well as technical program committees of several IEEE conferences. I welcome Professor Linga Reddy for delivering a talk. Thank you.
So I basically start with the very basics, so that you do not need any background knowledge, unless you sleep now here. But I try to make as active as possible. I start with very basics, then take step by step. You will mostly get what a radar can do. So before going to radar, we have other competitive sensors. For example, automotive or industrial, medical, or a vast number of applications. Basically driven by AI or ML. You using computer vision or basically sensor data, right? So you have RGB images. So RGB is very good when you have the daylight and very perfect lighting conditions. Then everything is okay. Then you have nice images and you will be able to do all the things. But if it is dark and all, then basically RGB fails there. Then when you move from RGB to, for example, night vision cameras or IR cameras, up to some extent, okay, they solve the problem. But these are all short range. When you cross approximately 10 meters, then you lose the clarity, right? You will not get many details, like when you are closer than 10 meters. So these are the RGB version and IR, the night vision. Then basically we have the thermal version again. Thermal version is also up to some extent solve the problems of RGB. For example, thermal works all the time because it basically works on the temperature profile of the bodies being imaged, right? So thermal is also quite good, but again the range is a problem. Then we have the lidars. The lidar is very good actually. Lidar works very well, but the problem with the lidar is large data. It is basically 3D point clouds. So you have large data, and also it is bulky, and we need a lot of power consumption actually. You cannot put lidar that easily on any system. But for static applications, lidar is okay. Even for industrial applications, it's okay. So after lidar, then we have the ultrasound, right? So ultrasound works very well, especially very short range. Medical imaging has a lot of applications, ultrasound. But on the other hand, if you want to use for automotive or industrial applications, the range is very short. For example, if you take the automotive application, it is basically used for parking, right? So this is the range of the sensors we are talking about. On the other hand, radar is a unique sensor, very unique, right? So when you take RGB or when you take IR or when you take up to some extent LiDAR, they all give the image. You get many details. But when we want to talk about the dynamics, for example, the range and all, you'll basically get with the LiDAR. But if you want to get the dynamics, like what is the range very accurately, and what is the velocity of the targets of the target in front of the vehicle or in front of a radar, basically. Also, where exactly it is located, it is basically called localization. Basically locating so and so XY position, so and so angle with respect to, that is called localization. Also tracking. These are all possible with the LiDAR, with the millimeter radar. No other sensor give very as accurate as the radar. So especially the range, the velocity are pretty accurate with radar. And the beauty of radar is it works all the way up to 400 to 500 meters. In night, in snow, in rain, fog, dust, every adverse weather condition, the radar works pretty accurately. We have tested outside. So I think from now on, if any system that needs dynamics, okay, the radar plays a big role. Radar will become an important integral part of the sensing systems, especially automotive, industrial, also medical. So there are many applications of the radar. Wherever you want to observe the dynamics, wherever you want to see the small changes, small vibrations we want to observe, either track the objects accurately, or locate the objects accurately. Radar is the most reliable sensor as compared to all other. But of course, you will not get image. You will not get image, right? So you can possibly fuse the RGB camera or IR camera or a thermal camera. Then you will get the perfect static information as well as dynamic aspects of the targets. Also the full details of the targets. For example, radar cannot tell what is the object, what is the shape, what is the size, and all that. You will get with the image. For example, RGB or thermal. Also, you will get the information about the object. So when you look into, so these are the things. So this you can freely download. This is basically various comparison I am talking about. All the things I am talking about. When you look into the radar, it is basically very reliable. It is having many advantages as compared to the other sensors I talked about. I'm not comparing with the imaging one, so but we'll look into those things. Okay, so that is the very quick introduction about the positioning the radar with respect to other sensors. So I start with very basics. You really do not need to know any basics to be able to start with the radars, right? So I start with very basic about how to estimate the range. Then the more important aspect of the phase of the IF signal. I talk about IF signal. So what is the IF signal is about? I will tell each and every word there. Then we look into the velocity estimation. Then the angle of arrival estimation. So when you know the range and when you know the angle, basically when you place the radar like this, the angle is basically left or right. How many degrees? That's basically called angle of arrival, right? When you tell the range is basically how far the target is. It's basically radial range. The radial means you have the center point here. If you basically draw the circle, all the points on the circle line are basically the radial points. The shortest distance from the center point of the radar to the targets is basically radial, basically on the circle, right? Radar gives only the radial range. Okay, that's the meaning of radial range. Then the word FMCW means it is frequency modulated continuous wave. I will give the brief details in the next few slides. Then basically velocity is velocity, how fast it is going, right? Then we have the angle of arrival, right? So these are the fundamental aspects of the radar. When you take the basics of the radar, how to estimate all these basically three parameters: a range, a velocity, and angle of arrival. Then Basically, I look into two applications. If time permits, I will basically definitely cover the first application. I will see how much time we will be having. I would like to cover the second application as well. That is basically the medical application. So the same medical application can be used for industrial application where you want to monitor small vibrations, be able to tell with what amplitude it's vibrating, with what frequency it's vibrating. If it is a bit abnormal, then you can basically sense in a bit advance, right? If you have any questions, you do not have to wait until the last minute. You can just basically stop and ask. Okay. So before going to the next slide, radar basically sends the beam, right? The beam basically it is like this. So you have the horizontal width. Horizontal width is this one, and you have the vertical width, right? Horizontally, the beam is very wide. Vertically, the beam is very, very small. So it means that you have the wide field of view. The radar will be able to see the things in a wide field of view in the horizontal direction, not in the vertical direction, right? Usually, we have the field of view up to 160 degrees. A small portion is left because the signal cannot go all the way to the left and right, right? When you fire the signal goes basically front side, not completely 0 to 180 degrees, right? So that's the reason you have mostly up to 160 degrees. On the other hand, the vertical side, the beam width is very small. We have approximately 30 to 40. It means that if the targets are not there within this 30 to 40 degrees in the vertical direction, the radar will not see. However, you have large field of view in the horizontal direction, right? That's the field of view I'm talking about. All the things I'm going to talk about, the field of view is basically horizontal field of view. I'm not talking about vertical field of view, right? All the things I refer to the horizontal field of view, right? Then basically what radar can do is that radar can tell how much is the range of the target, how much the velocity with how much velocity the target is moving, where exactly the target is located with respect to the radar. That is angle of arrival, right? Then we have three more important definitions to be able to understand clearly what the radar is capable of, how to read the radar data sheet, or how to tell how good the radar is. There are three more important definitions. It's called the range resolution. Then we have the velocity resolution. Then we have also angle of arrival resolution, right? The range resolution means how close two targets can come. Still, the radar sees them as two distinct objects. For example, if a given radar's range resolution is, say, 5 meters, if two objects are closely spaced 4 meters apart, then radar sees them as single target, right? Because radar is not capable of resolving that one. Radar can only resolve 5 meters and above. That's what is the meaning of the range resolution, right? Ideally, how much range resolution we would like to have? How many meters? Yeah, all the way down to 0, right? all the way down to 0 is the ideal one, but we will never get, right? Then we have the velocity resolution, right? If you go one step ahead, the velocity resolution is also similar definition. If two targets, how closely the velocities can become, still the radar sees them as two distinct velocities, two distinct targets with two distinct velocities. For example, if two targets are at the same range, are approaching radially towards the radar, if the velocity difference is very small, for example, the velocity resolution, I say that 1 kilometer per hour. If radars are moving with 10 and 10.5 kilometer per hour, then radar sees them as targets moving only with single velocity. There is only single target moving with one velocity because the radar is not capable enough to be able to see two targets with two distinct velocities. That's the velocity resolution, right? Then the final one is angle of arrival resolution. So it is also similar definition as when you look into the range. the angle of arrival resolution is basically when you split the field of view, for example, 0 to 180. If the field of view is 180 degrees, if I say that my radar resolution is 30 degrees, right? If there are two targets forming a cone are placed within the 20 degrees, for example, then the radar sees them as a single target. If they are only more than 30 degrees apart, then only radar sees them as two distinct objects, right? So these are the fundamental definitions to be able to go further. Is there any question for anybody? If something is not clear, I will try to repeat, because nobody will explain these things. I told, for example, but I will get into the numbers of the radars what we use. Limited number means it is basically based on the resolution. I will get into those details all with examples and all. You will get a quite intuitive understanding. I will show all the numbers also. Okay, but these are the very fundamental basics. Definitely, radar will take a dominant position in the sensors domain. Definitely, because it is so accurate in the range, so accurate in the velocity estimation, very perfect for long range in the adverse weather conditions. Only that is the reason. Mostly automotive, industrial and medical. Several applications are there. Okay, I'm starting all the way from ground. Okay, what is the radar signal? What we use basically FMCW. It is frequency modulated continuous wave. Any signal, if you basically you have the amplitude and frequency and phase, right? So here basically the amplitude is constant. We basically linearly increase the frequency. So this one is basically when you look into the time domain, it is amplitude and time. You basically increase linear. The frequency is increased linearly because the frequency is low here. So as you go, it is increased, right? So this is amplitude versus time. The same thing can be looked in the frequency domain. The frequency versus time, you basically linearly increase. Frequency, you are going linear. So when you look into what is the slope of this one, is basically how much you sweep in the frequency, how much frequency you go from starting to the highest frequency, and then in basically in how much time, right? You can vary these parameters in the radar while configuring the radar. You can basically vary the bandwidth. You can vary this time as well, right? So usually millimeter wave radars operate in the gigahertz range. The radars basically the TI series which releases, they operate in 77 to 81 gigahertz. 77 to 81 gigahertz. The difference 81 minus 77 is 4 gigahertz. It's called RF bandwidth. It is radio frequency bandwidth, right? So this is the signal actually we transmit. We transmit a range of frequencies, right? Ideally, one frequency is good enough to be able to do. One frequency also you can basically do the radar, but we do a band of frequencies because we want to resolve as many things as possible, the closely spaced system. That's the only reason we send a span of frequencies which is called RF bandwidth, right? So when you look into this one, the 4 gigahertz is swept over 40 microseconds. Basically the slope is basically 100 megahertz per microsecond. This slope is the parameter that will decide something later. Okay, if any question, just stop. I want to transfer some knowledge, right? I'm not rushing. Definitely radar. It's high frequency.
What order generally?
I'm
Energy in signal.
we actually have power. We did not really, we could not measure. We have the oscilloscope to be able to measure up to 110 gigahertz, but we have never got a chance to look into. We're not sure about the amplitude, but the power is very small. Very small. You can basically operate with the power bank of the mobile phone. You can just really take the radar outside and you can connect it to the PC and you can just power up with the power bank.
These are small handheld devices.
Huh?
The TI radars,
yeah,
they are handheld, very small devices.
Very small. You can just put it in the pocket.
Okay.
Yeah, very small radars. So that's the reason. That is the only reason radars became very popular. Very recently, this field has emerged very recently, not even 5 years. Not even 5 years. Before that, the radar is a big thing,
Yeah.
right? You need to have a big setup.
Yeah, that's what many may be wondering, that it's huge radars actually.
Yeah.
These days we have all the small ones.
All the very tiny version.
Tiny ones.
Yes.
I have a doubt from the initial slides
Yes.
where we are talking about ultrasound versus this radar thing.
Yeah.
So what we right now use for parking purpose and all these things are the ultrasound based ones.
Short range. Yes.
Short range.
Yes.
But probably when it comes to this automotive car driving, because you need to look for too far, that is where these radars will be used.
Medium and long
But
range.
the approach used, is it similar that they use similar to the chirp signal, which has multiple frequencies, and then you get the you estimate the distance and all, or maybe a different mechanism is used? I mean, to measure the distance.
To measure the distance, they basically use the band of frequency. It is the same.
Similar
Same concept.
thing is used.
Yes.
And is there any restrictions on using these frequencies and these radars as
No.
such, or can be used by anyone, anywhere kind of stuff?
Anyone, anywhere.
Okay.
No problem. But not for military. You can buy the small radars. They do not take NDA.
Okay.
But they are also selling. They are also selling the imaging radar.
Okay.
I don't think they are selling that easily now, because you can do many things with that.
Right. That's
Yeah,
what.
so-
Similar to the ultrasound, which we can't buy as such the certain probes.
Yeah.
I was wondering maybe because of the frequencies it uses or potential applications it has.
No, this is 77 to 81 gigahertz is ISM,
Okay.
so it is free band.
Free band. Fine.
You can do many things actually. You can actually, even with that small radars also, you can, if you want, you can do.
Thanks.
Yeah, right. But on the other hand, imaging radar has a lot of potential. You can literally do many things. Yeah. So I have not yet started the range estimation. Okay, is anybody getting sleep? Any questions here? Because this is the main slide. This is the main slide to be able to go further. So it's basically a fundamental signal, right? Basically FMCW signal. It is basically going. I basically looking most of the time in the frequency domain, not in the time domain, right? So we basically look in the frequency domain later on. Okay, how the radar works basically? We generate the signal, then we basically transmit. If there are a couple of objects in front of the radar, you basically get the reflection, right? So there's a transmitted signal. If there are 10 targets, you basically get 10 reflections back. You will be firing only one signal, but you will get 10 reflections back. Then you take this transmitted signal and all the reflections, then you mix it here, then you basically generate the intermediate frequency signal, right? All the processing, what we talk about the radar signal processing, is processing this signal. Even though the radar is operating at 77 to 81 gigahertz, when you do mixing, the signal coming out here is basically on the order of couple of tens of megahertz. We came all the way from gigahertz to a couple of tens of megahertz. When the moment the signal is in a couple of tens of megahertz, it's very easy to digitize. There is not much strict requirement on the analog to digital converters. On the other hand, if you will have to use the gigahertz range, then sampling and all will become difficult. Okay, this is called intermediate frequency. This bandwidth is much smaller, right? So what all we process about the radar is basically this signal. So this signal is basically when you have, for example, this mixer is basically, if you send two signals, the signal one is x1, the signal two is x2. The output is basically what you get out of the mixer is basically the difference of the frequency, basically instantaneous difference of the two frequencies. What we input basically to the mixer. Then the phase is basically the phase difference. The definition of phase is basically that is associated with the starting of the signal, right? That is basically difference of the two phases of the signal, right? That is the signal we get, right? So if we look into the frequency domain, basically the same thing what I explained. If you look into the frequency domain, so this is a frequency versus time. So as I told, so this is a transmitted signal. That is also called chirp, right? You should not get confused with the multiple terms. a transmitted signal or a radar signal is also called a chirp, right? You basically send this one. Then, if, for example, if there is only single target, then after tau seconds, we get the reflection. This tau is basically the time it took for the transmitted chip to go and get the reflection back. That is basically two times the distance over the velocity of the light, right? Then we get back the reflected chirp here. What the mixer does is basically take the difference of these two signals, right? When I take the difference of these two signals all the way, when these two are there all the way in the time domain, so in the time, if you take the difference is constant actually, right? If you look into the frequency domain, same frequency domain, the signal is a constant tone frequency if there is a single target, right? So this frequency is basically directly related to the how far the target is. The frequency of the IF signal is related to the range of the target. Okay, what is this frequency? If I form a triangle here, so the slope is S here. On the x-axis, this is the tau. So y is equal to mx, right? It is basically starting from the origin. The slope is basically s tau, right? The slope is the frequency, right? No. The difference is the frequency, right? So the frequency of the signal is basically s tau. That is basically s 2d over c. If you basically know the frequency of the IF signal, basically you can translate the frequency to the range. That's how you estimate the range, right? That's a very fundamental in estimating the range. How you do practically? How you do in the real time, in the real life? You basically configure the radar with certain RF bandwidth. You basically transmit the chip. You basically get the reflection. You basically log this IF signal. You basically sample this IF signal. You basically get the samples. You basically take the FFT. Then you look for the peak frequency. That peak frequency is translated to the range. That's it. Very simple signal you take. It is basically simple sinusoidal signal. It is sampled at certain sampling rate. Okay.
IF signal you told it will be in megahertz.
Yes.
So S is some gigahertz per
megahertz per second, right? Megahertz per 10 microseconds.
S is
This is 100 megahertz.
100
per
megahertz per megahertz. Okay.
Right.
So we will be transmitting like pulses.
No, it is
of continuous radar.
Continuous FMCW signals. A series of FMCW signals.
So we need to be continuously tracking that IF signal and keep on calculating.
Keep on dynamically, okay. Yes.
Okay.
How often you want to, up to how you configure. You are free to configure. Whether you want to fire 5 chips or 10 chips every 5 seconds or every 5 minutes. It's all up to you. You basically get the samples from the ADC. Those samples you log. You basically take the FFT of that. So that's how you estimate the range for a single target. For a single target, basically you need one transmitter, one receiver, one FMCW signal. That's it. What if there are multiple targets? What if there are multiple targets, right? So before going to how to basically estimate the range of the multiple targets, before going to that, we basically look into the fundamental aspect of the FFT. So when you take the sinusoidal signal, when you take the FFT, it basically gives the frequency domain, right? It basically tells the frequency components. So when you take the time domain signal, so when you apply FFT, you basically get the frequency component, right? So that's very well known. So for example, when you take the two signals, there are basically two signals there. One is the blue signal, the other one is the red signal. The red signal completes only 2 cycles, so it's going from here but on the other hand, blue signal goes a bit more, right? Only half cycle more. When you take FFT, you basically see the single peak, right? On the other hand, if you double, you basically double this time. So when you take the FFT, you suddenly see the two peaks, right? So this difference is basically, it will become smaller and smaller if you have the longer and longer time period, right? That's basically 1/t. If you want to observe a small difference in two signals, why we want to observe a small difference in two signals? Any guess? Huh? Yeah, right. We want to distinct the closely spaced objects which are not limited by the fundamental limitation of the radar, right? So that's basically coming from bandwidth. We will look into that one. So if you are limited by the FFT, then you are not touching the fundamental limit of the radar, right? Right. So this basically, yeah. So this basically, the longer the time period you have, the more closely spaced frequencies you can observe, because we want to look into more closely spaced frequencies, because the more closely spaced objects will be projected onto the frequency domain into the more closely spaced frequencies. The more the closely spaced targets, the more the closely spaced frequencies. As long as we can resolve the more closely spaced frequencies, then we will be able to resolve the more closely spaced targets. That's our intention, right? So this is basically coming from the fundamental limitation of the FFT. We're not doing anything, right? It's basically 1/t. The more the time is, the more closely spaced targets we can resolve. It means if I want to resolve two closely spaced targets, I basically send a long FMCW signal. When I send the long FMCW signal, it's basically I'm basically increasing the RF bandwidth, right? My RF bandwidth is going to decide how closely spaced targets I can resolve. That's a fundamental limitation about the resolving the capability of the radar. So if there are multiple targets, you basically get the multiple reflections. You basically get the multiple frequencies in the single IF signal. If you take the FFT, you basically get the multiple peaks. You basically convert all these peaks to the range. S 2D over C is equal to these frequency peaks. You know the S, you know the C. You basically know these frequencies. You basically get the range of the targets, all the targets in front of the radar, right? So, any questions so far? No, but you cannot generate a large range of frequency rate. That's the problem, right? You cannot. You can more energy to generate also, right? More energy, more samples, everything gets increased. Yeah, yeah. No, usually the longest range target. For example, if the radar says that the data sheet says that this radar works up to 300 meters, basically they refer to car or the truck, not the humans, obviously, basically truck, right? So 300 meters or 350 meters or 400 meters, the reflection it takes is only 5% of the total chip. For example, 40 microseconds is the chip time. If we are swapping the 4 gigahertz in 40 microseconds, the longest the located object, the longest range, for example 350 meters or 400, whatever it is, it takes only 5% of the 40 microseconds. It's about only 2 microseconds, right? 2 microseconds. Yeah. So there's no disadvantage actually in sweeping, but only disadvantage is that we cannot make such long frequencies, and it takes more energy, more samples, more processing, and everything. It's a challenge. That is the reason the mmWave radar came out very lately after we were able to integrate so many things. If you look into millimeter wave radar, the fancy thing is about the antenna is just a dot, like a bindi. So it is a very small dot, the antenna. Yeah.
What happens if the target is moving?
Target is moving, it is dynamically doing, right? We are doing in the microseconds. Target moves in sub 1 second.
Okay.
Right? So we are doing
this
the
is used in automotive radar.
Yeah, right.
So
we are talking in terms of microseconds, 40 microseconds. It's not even, we're not even entering into milliseconds, right? It is ultra fast. In processing also, it's only FFT. It's not a huge algorithm. FFT is a very super fast algorithm, right? It's only FFT.
And get the range. This will repeat.
This is continuously done. Yes, continuously done.
Okay.
In the microseconds.
Yeah.
So no problem. So it works very well for automotive, because we do all the processing also. Processing also will be done on the order of microseconds only. Couple of tens or
Now the array of radar signals are sent for getting the distance and all, or single?
No.
Okay.
You do not need array.
Okay.
Array is needed only for angle of arrival. Right? Very fancy to work with radar. You basically, when you have radar, you can really see the things working. So radars will work very well with the drones as compared to on-road vehicles, because you have multiple reflections on road, but on the other hand, for drone you have only birds, right? And you have free space. You will get much more accurate measurements, right? But there are several other research problems in this. Basically, when you have multiple radars working in the given vicinity in the small range, you have the interference. So that's a completely different domain. Even for LiDARs or GPS, spoofing techniques are there. People are intentionally spoofing. So that is completely different area. People probably intentionally create the interference for radar too, sooner or later, definitely. Right? So how close we can go? What is the fundamental limitation? How close we can basically resolve? That is basically coming from the fundamental definition. As I said, the difference of the frequencies is greater than 1 over TC, right? The longer the TC we have, the smaller differences we can observe. So if you basically replace this delta F, basically S to delta D over C, if you rearrange all these things, you basically delta D is C over 2B. 2B is the B is the RF bandwidth, right? So if I sweep, obviously intuitively, if I sweep very long, I'm basically increasing my time space. I'm basically, that 1 over T is getting smaller and smaller. Then I can see more and more closely spaced targets. So the larger the bandwidth, it basically completely depend on only RF bandwidth, right? So when I get into the numbers, basically 4 gigahertz RF bandwidth, the resolution we're talking about 3.75 centimeters. So targets can become as close as 3.75 centimeters. Still, radar sees them as 2 distinct objects. If it is only less than 3.75, then the radar cannot see. Radar sees them all as a single target. This is, I'm talking about different radial distances. But if there is another limitation, if there are 100 targets on the radial range, same radial range, radar sees them all as a single target. That's a drawback for the radar, right? But it is very rare chance, unless someone intentionally want to attack something, then they can coordinate and they can go by maintaining the same radial range. They can approach some source. It is possible, right? So that's another fundamental limitation of the radar. When you start working, you will get to know. Yeah. Velocity also can be resolved. Angle also can be resolved, but there are fundamental limitations. So the limitation for range resolution is basically bandwidth. Then the velocity resolution, there will be another limitation. For angle of arrival, there is another limitation. I'm just giving what is the top and bottom we can do with the radar, right? What are the extremes we can do with the radar? What we can actually get out of it, right? So this is a fundamental limitation. When you are working with 4 GHz bandwidth radar, you cannot resolve below 3.75 centimeters. That's a fundamental limitation, right? If somebody tries to do the small experiments for small things for radar, you cannot do below 3.75 centimeters. One has to read that one properly. Obviously, when you are buying radar, when you want small resolution, obviously you look for the, okay, what is the RF bandwidth? Okay, 4 gigahertz, then you have the 6 gigahertz, same price. Obviously, you pick up the 6 gigahertz one, right? That's how I want you to get that intuition, right? When you're looking at the radars, right? Now, TI has released a lot of radars. You obviously, when you look into, right, you obviously, some may have 2 gigahertz bandwidth, some may have 4, right? Okay, the more bandwidth, the more I can resolve, right? So that is what is the intuition, which is related to the RF bandwidth and the range resolution. Okay, then how far we can see? There is another fundamental limitation. What is the longest object I can see? So what is the longest I can see is basically coming from the two fundamental limitations: how much power you can pump and how much how much basically can come back, right? If you pump basically very small amount of power, it doesn't matter how close or how far it is. If you do not get any reflection back, then obviously you will not see any longer distances, right? So that is basically physical fundamental limitation coming from the how much power you can use. On the other hand, you are getting IF signal, right? That is having certain frequency, right? Certain band of frequencies, because you are basically pumping band of frequencies. If you have multiple targets, multiple reflections, you will also have the noise. You basically IF signal will also have certain bandwidth, right? If you basically your analog to digital converter bandwidth sampling frequency is basically deciding what is the maximum the frequencies you can basically process, right? That is another limitation I'm talking about. That limitation is basically the sampling frequency times the velocity of light over 2 times the slope of the chirp, right? It is basically directly related to the sampling frequency of the ADC. The more the sampling frequency of the ADC, the more frequencies you are able to sample, the more you are able to process, the longer the objects you are able to process. After all, the longer the frequency of the IF signal, the longer the range is, right? The smaller the frequency of the IF signal, the shorter the range is, right? It's very easy sensor to be able to work with, right? So this is basically summary. I'm not just repeating anything. Any questions on this, right? The range is clear, right? Tunable. Tunable. Slope is tunable, and you will never fire a single chip. You basically fire a series of chips called frame. That is also tunable, and how often you want to fire also is tunable. So there are many things you can basically configure. There are quite many things you can configure, right? So far, we basically looked into the IF signal, only frequency, right? The IF signal as the phase. Frequency is basically giving the coarse information, not very fine information. The large changes in the distance are basically visible in the frequency. Very short changes on the order of millimeters are not visible in the frequency. Why? Very small changes in the targets are not visible in the frequency, because we do not have basically enough bandwidth, or we're not taking the measurements for enough time to be able to resolve in the frequency domain. There is so little, that time is so little, or that measurement is very small, and that frequency is also very small. The difference of frequency is also very small. We are not able to resolve, right? So then the the phase of the IF signal is basically the key parameter to be able to look into the velocity of the targets as well as the angle of arrival of the targets. Okay, then we look into the phase. So when you take FFT, basically you will get the frequency component as well as the phase component, right? So when I take this FFT, you basically, if you have the same signal, same frequency, but different phases, you basically get the frequency peak at the same location, but the phase will be different, right? So when you look into these two signals, so the phase definition is basically starting, you look into the starting of the signal, right? So this is basically 0 when you look into sinusoidal signal, right? When you look into this one, the phase is basically 90, right? So when you take FFT, the frequency peaks are same, but phase is 0 here and phase is 90 here, right? This phase can be used to capture very small movements of the targets. These small movements, I'm talking about heartbeat, breathing rate, small mechanical vibrations. So all these sub 1 millimeter range also can be captured in the phase, not in the frequency, right? So these small changes are used to these small changes captured in the phase can be used to estimate the velocity of the targets as well as angle of arrival of the targets. Okay, I will directly move on to here to be able to tell intuitively what this phase is. Basically, you have the signal. The starting of the signal is basically, for example, if you consider this is a one time period, right? If I basically shift this signal by one time period, what is the phase difference between these two signals? This original signal and the shifted signal by one time period, 0 or 360, right? 0 or 360. If I move less than one time period or 0 to 1 time period, what is the range of the phase I can vary? 0 to 360. Yeah. So if I put that into the equation, this is basically 4 pi f delta tau. This is basically 4 pi delta d over lambda. Lambda is basically the wavelength, right? So this is the phase difference between two IF signals, right? This is the phase difference between two IF signals. It is basically a very basic thing. I'm just I'm taking two sinusoids. I'm basically taking the phase difference. Okay. Right? How to, why we are looking into the phase difference? For example, when I take a 1 millimeter change, the object changed by 1 millimeter from the present position to the next position. The change is only 1 millimeter. First, I look into the frequency domain, how much frequency it is changing. It's basically S 2 delta D over C. So when you do the math and all, you will get 333 Hz. When you look this 333 Hz in the 40 microsecond time window, this is translates to 0.013 cycles. That is so little, right? If you take FFT, this is not at all visible. On the other hand, if you take the phase change, that is approximately 180, right? It is close to 180. Means very minute changes are visible in the phase as compared to frequency, right? Just 1 millimeter is giving the 180 degrees phase change. If it is sub 1 millimeter, it is obviously between 0 to 180. Okay. Yeah. To be able to estimate the velocity of a single target from the radar, you basically fire one FMCW signal. After TC, you fire second FMCW signal. You basically get the first IF signal from the target. You get basically second IF signal from the target. You get two IF signals. You take the FFT. Target is more or less at the same range in the frequency domain. You get the peak at the same frequency, but the phases are different. You basically take the difference of the two phases. Then within this TC, the target is moving with velocity v, then the target would have moved vtc distance, right? If you equate the phase difference into this formula, then you will get the velocity. The phase difference is captured to estimate the velocity of the target. That's it. Okay. For this, we need one transmitter, one receiver, at least 2 chips to be fired. Okay, it is fine. There's only single target. There's only single target. I fired 2 chips, then I get 2 IF signals. Then I am able to estimate the velocity of that single target. What if there are 2 targets or 3 targets or multiple targets? What should we do? For example, if there are 2 targets, you will get only 2 IF signals. The 2 targets is only giving only a single phase. That is unresolvable, right? Because that is embedded in the single IF signal. And what is the solution? You fire multiple chips. You fire multiple chips basically, right? If you fire multiple chips, you basically get the multiple IF signals. You take the second FFT on those IF signals again. You will get the phases associated with those. If you have 10 phases embedded in it, you will basically get the 10 peaks, 10 phases, right? That is how we estimate the angle of arrival of the multiple targets.
What is the range of phase and delta phi? Will they be within -π to π or 0 to 2π, or they can exceed?
No, they cannot exceed 0 to 360.
So there is no graphing and ungraphing.
No. It has to be the unambiguous. The phase is only 180, right? Either target has to come or go, right? One way is coming and the other way is going. It is only 0 to 180 or 0 to -180 or 180 to 360. Yeah, that scenario doesn't occur. It is so small, so small distances are captured because on the range of millimeters actually, right? That scenario doesn't occur. It is very well working with range and velocity. It is pretty accurate, very accurate, up to whatever the data sheet says. It is working pretty accurate. Very fast moving targets. Very fast moving target. Yeah.
This possibility is there, or
Yeah,
so
if
you
somebody
fire and then you are waiting for it, but in between there is an obstacle.
yeah,
So
if
generally
there is
not-
obstacle, it's yeah. If
And then it's a dynamic obstacle in going back. Then whatever you say, probably Dr. Ramakrishna, whatever he's saying. Probably.
yeah, if you have unknown things and very close dynamic and all those things, that have to be tackled.
Because
it's not,
the frequency at which you are releasing the chip signal.
Yeah.
And the portion is the
that portion is there, but you are going to average quite quickly. You basically send the frame, for example, 128 chips or 256 in a frame or 64 chips in a frame. You basically average over 64. You are doing quickly immediately another frame. Maybe one or two frames you will see that problem, but over other couple of frames you basically pass the target, right? You will basically get pretty much faster estimations. That the momentary things are not a problem.
Because in mobile robot applications, the chirp signal power is important.
Yeah.
Because you cannot just release the highest amount of power assuming environmental conditions are the worst.
No.
So
Yeah.
you check the environmental conditions, then you fire the chirp signal, and then you take it back. Depending on the, I don't know.
They have not evolved up to that much.
Okay.
They have standard settings and that power is very minimal actually. I'm telling that we have done most of the measurements only with the power bank.
Okay.
Power bank. And some of my students are now putting onto the drone.
Because most of the time LiDAR takes care in mobile robots.
Yes. Okay. And some of my students have done the breathing rate and heart rate. It is pretty much accurate. it is very well working. Yeah, you can clearly see if somebody is breathing faster, the radar is basically telling. So, okay. So, for example, if you have very periodic signals, for example, vibrations, for example, a mechanical thing is vibrating and you want to estimate whether there is abrupt changes in the frequency or amplitude of the vibration, the radar is a pretty accurate device to be able to estimate that one, right? All these distances will be translated to the phases. When you basically looking into this one, so it is basically the amplitude of the phase can be estimated. Also, if you take the FFT of this one, you can also get the frequency associated with the vibration, right? In the industrial environment, most of the people for vibration monitoring, people started replacing all the old stuff with the millimeter radars. You can observe sub 1 millimeter amplitude vibrations also, sub 1 millimeter, not in the nanometer range, but in the millimeter range, right? Yeah. So when you basically visualize what I'm talking about, the velocity estimation for multiple targets, you basically fire multiple chips. You basically take the first FFT, then you take the second FFT, then you get the, if there are 10 targets with 10 different velocities, you basically get 10 peaks. Then you basically take those phase differences, then you basically estimate the velocity. Okay. Any questions on this so far? You basically first FFT is complex numbers. You basically run the second FFT on the complex numbers again. Yeah. No, you basically take the, you are taking again the FFT on the complex numbers only. Yeah. So the angle of arrival goes. You see, they now there is a fundamental limitation for there are fundamental limitations for the velocity estimation. How fastly moving targets you can estimate, how closely moving velocities of targets you can estimate. I'm not getting into all those details, but all the math are there in the slides. Right? I'm not sure how much time we have. Okay. Yeah. So, but these are key aspects basically with respect to radars. Definitely, if somebody is working in the sensors and signal processing or automotive, industrial, medical, at some point of time you will definitely encounter millimeter radar, whether you want it or not, right? Because it is so reliable in range and velocity estimation. There is no physical fundamental limitation on that. For the range resolution, we have the bandwidth that is deciding the range resolution. For velocity estimation, also how fast you can fire the chips, that is basically deciding. If you want to move fastly moving targets, you basically need to fire the chips so fast, not 40 microseconds, but you have to cut down a little bit and you basically fire, right? So very well, those are not demanding a huge hardware, not too many. We are not talking about antennas. We talked about only one transmitter, one receiver, basically one antenna, transmitting antenna, one receiving antenna, both for range and velocity estimation. That is good enough, right? Just one transmitter, one receiver. For range estimation, you just need to fire one FMCW signal. For velocity estimation, one transmitter, just one transmitter, one receiver, multiple chips, right? On the other hand, angle of arrival estimation is a bit challenging. You need a little bit more resources. So I'll come to that one now. So the basic definition of angle of arrival is when you have a radar like this, basically to tell with respect to radar, is it plus 30 degrees or minus 30 degrees, basically left or right, how many degrees left and how many degrees right. It's not telling how many degrees top and how many degrees bottom. It's only in the horizontal field of view, horizontal only we are talking about. So also, what is the maximum you can see? Basically, theoretically, you can see left 90 degrees and right 90 degrees, not more than that, right? Because because the transmitter is sending the signal towards this side, you cannot see backside, right? So the theoretical limitation is basically -90 to +90. If I have radar like this, radar can see from 0 to 180, right? So that's the maximum one. So we basically use the phase only, the phase change only we basically use, right? So to be able to estimate the angle of arrival, we need at least one transmitter and two receivers, right? So there is one transmitter here, there are two receivers here. When you have a transmitter here, if there is a target here, the first receiver is basically d distance, but second receiver is basically placed a bit distance away from the first receiver. The reflected signal will travel delta d distance additional as compared to the first receiver, right? How much is this delta d? This delta d will basically result in the phase difference of 2 pi delta d over lambda. But earlier we see that the phase difference was actually 4 pi delta d over lambda. Why there is a 2 difference here? For a delta d change, we have 4 pi delta d over lambda here, the phase difference, and here we have only 2 pi delta d over lambda, right? 2 delta d, yeah. It has traveled 2 delta d here, so that's why we have 4 pi delta d over lambda. Okay, so one guy is following very nicely. Okay, yeah. So 2 pi delta d over lambda. If you know this delta d, we have to associate somehow with respect to the radar how much the angle. If you translate this delta d into the angle, then this phase can be converted to the angle, right? That's what we do in the traditional basically angle of arrival estimation. Okay, so when you do more closely, for example, if there is a target here, so this angle of arrival is theta. So when you do this one, when you draw these lines and all, so this is theta, so this has to be 90 minus theta. If this is 90 minus theta, then this has to be theta, because the total has 90, right? So this additional distance is basically d sin theta, right? If you replace the additional distance with d sin theta, if you rearrange into the math, the angle of arrival is basically sin inverse lambda delta pi over 2 pi d, right? It's fine, working perfectly fine. There is only single target. You have one transmitter and two receivers. You basically take the phase difference, and that phase difference is basically translated to the here. There is a difference between the velocity estimation and the angle of arrival estimation. Velocity estimation, you have only single transmitter, single receiver. You basically fire the two chips. Here, you have one transmitter and two receivers. You basically fire only one chip. You still have two IF signals. You basically take the difference of the phase of two IF signals. Then you translate that to the angle of arrival. What if there are more than one target? What should we do here? Multiple chips will work, or multiple antennas? Multiple receivers I need. I'm talking about spatial domain here, right? The velocity estimation, you simplify the multiple chips. But here, if I want to get the more phases embedded in the signal, I need more physical antennas. The more physical antennas will tell how closely spaced targets can be resolved. The more the number of, for example, if I have large number of antennas, then I can resolve very closely spaced targets, because I'm able to resolve those phases in the second FFT. So the velocity estimation, the angle of arrival estimation, the procedure is exactly same. For velocity estimation, you basically use one transmitter, one receiver, you basically fire multiple chips. For the angle of arrival estimation, you basically have one transmitter, multiple receivers, you fire one chip, you get multiple IF signals across multiple receivers. You basically take the second FFT on that. You basically take exactly to the same procedure. Here, the delta d is translated to the angle, the delta d is translated to the velocity. That's it. Those are the fundamental aspects of the millimeter wave radars. These are the traditional processing. So only drawback is, if you want to tell the angle of arrival of the multiple targets, there is a physical limit. We cannot put the infinite, you cannot put large number of antennas. That is the only drawback for the mmWave radars. You cannot localize the target, especially multiple targets. We cannot localize very accurately. That's a limitation, right? But this limitation can be we can overcome this one by fusing, for example, RGB camera, a thermal camera, or an IR camera. You'll get the pictorial information. That pictorial information can be translated to the angle very easily. If you know the field of view, if you know the horizontal field of view and vertical field of view, you can easily map the angle with respect to as if it is a radar, right? That's not a problem. So that is the reason where it is pretty accurate over the range and velocity. Anyway, we will not get, we are not interested in the shape and size because it is too much to be able to do with the radar. We can simply keep one RGB camera, you will get a nice pictorial information, or IR camera, or thermal camera in the worst case. You will get a nice pictorial information. You can get the object features there. And also you can estimate the velocity. You can estimate the angle of arrival by overcoming this limitation. If you will have to do only with the radar, that is not very accurate either, because this phase is not linear. On the other hand, velocity, the phase relation is very linear, but here it is a sinusoidal, right? So when the target is right in front of the radar, it is pretty accurate. The phase changes are very sensitive to the angle. But on the other hand, when they are very extreme, there are no phase changes. The phase changes are almost diminishing to zero, right? Your estimation also will be not uniform throughout the field of view. That is also another fundamental limitation for the radar with respect to the angle of arrival estimation. So the angle of arrival estimation is not at all accurate when you do with the radar, surely, because of the fundamental limitation of the number of receiving antennas, the fundamental limitation of how the phase change is related to the nonlinear wave, right? So it's about the maximum field of view, all these things, and all these things I kept already. So it is more intuitively explaining the angle of arrival resolution. Also comparing the angle of arrival resolution, the velocity resolution, and all, and putting all the things together. But mostly when you look into, usually no targets will be closely spaced as close as 4 centimeters, usually more than 4 centimeters, unless somebody is intentionally planning to be able to approach some source by coordinating to be able to have the same rail range. Further, someone has to have the source information. Possible to do. Usually you should be able to, when you have the 4 gigahertz range, you will be able to resolve the things in the range, the first FFT. If not, if they are static, it can be static objects, right? But radar can move, right? Radar is moving. If they are more than 4 centimeters, the radial distance, you will obviously get in the range FFT. If not, if there are two distinct velocities, you will obviously get in the second FFT with respect to velocity, right? So as long as the objects are resolved in the range and velocity domains, you do not have to worry much about the angle of arrival estimation anyway, which is not accurate. Even if you do, that is not accurate. I'm pretty much sure about it. Okay, so that is the limitation of the radar, right? So where exactly we use radar in a foreseeable future, right? So basically, people started with the drone taxis, also delivering the medicines or delivering the groceries, all the things with drones. So you will quite soon see these operations will become very normal, right? You cannot put a very big radar everywhere to be able to track the things, right? we need a short range radar. So, for example, the radar I'm talking about is ultra cheap. So this can go all the way up to half a kilometer, right? Half a kilometer, one radar, it is such small radar is basically affordable price, right? So we can basically monitor small objects as well in the space. Actually, in the free space, we can basically radar works very well. Even the small targets like small drones, it's not the bird like very small drones, but you can the reasonable size like more than 10 centimeters by 10 centimeters or 15 centimeters. So it's very easy to track or easy to localize with the radar. But ultra, there are very small bird-like or those drones as well. Those are anyway are not possible with the RGB camera or thermal camera. It may be possible, but the range is very small for those, right? So there is no point in detecting somebody is very close already. Then you do not have time to react, right? For example, at least the radar, if you are able to detect up to 300, 400 meters, you have enough time to be able to take some decisions, right? But 10 meters, 15 meters is too small. Like for the RGB camera, IR, so those are like you need to be very close, like 10 to 15 meters or max 20 meters, not more than that. You will not get any information after 20 meters. You will get, but you will not get very small drones, like you will not get the information. So, you use hyperspectral cameras, right, from the drone. That is another domain. But what I'm talking about is tracking the drone, which is basically doing some service. I want to track all the drones. I want to locate all the drones so that the ground station has the complete information, so that it can be reported to. For example, if you want the drone, you basically put in service to be able to deliver something from take from point A and deliver at point B, right? And you want to monitor your drone. Somebody has to give the service. Somebody has to keep on updating your location and make sure that you will not collide, right? And somebody has to take in charge, right? Of course, if you guarantee yourself, it's fine. But if it falls somewhere, right? So somebody has to give more accurately the information, right? You cannot depend anyway on GPS. GPS spoofing is very huge these days. It's very easy to spoof the GPS. It's very easy to spoof the GPS than any other sensor. Of course, you can spoof LiDAR, you can spoof radar. So all these things are possible. So next phase will be how to accurately estimate or classify or segment in a spoofing environment. That will be next decade. Okay. So what we did basically, how to estimate multi-target angle of arrival estimation. We basically rotated the radar, right? We know that the range is pretty accurate, the velocity is pretty accurate. You can actually use the range profile or the velocity profile to be able to get the angle very easily. We basically what we have done is basically, I'm not getting into all these details I talked about already in the beginning slides. I will directly put go to the how what we have done. Basically, when you look into the literature, all that were published, basically to be able to estimate the angle of arrival of a single target, you need at least one transmitter and two receivers. So all these are like that. So this is the rotating radar we published very recently, where you need one transmitter and one receiver only to be able to estimate the multiple targets. It is not for free, but we are basically rotating. We need to rotate the radar all the time, right? So what we have done is basically we have put the radar on the rotor. Basically, this rotor is basically for taking the pictures by putting the mobile phone. Basically, that rotates and takes the 360 picture. Basically, we bought that one and we put our radar there. Then the radar can go around, right? So what basically we have done, basically how we have done the angle of arrival is basically, we put the radar, we use only one transmitter, we use only one receiver. We know that the radar horizontal field of view is more, the vertical field of view is small. We basically tilted the radar by 90 degrees so that you get the more vertical field of view. Then we basically scanned by rotating. We only used one transmitter and one receiver. We basically get the range profile. If there are 3 or 4 targets in the same angle, then we get those information as well. But that is not possible with the ordinary angle of arrival estimation. Then we basically rotated and we put the ground truth, and several people and several drones, several cars are there in the scenes. We repeated these measurements and we made the large data set, right? Then, for example, if I am rotating 0 to 180, if I am firing 180 frames, then I'm putting the angle 0 to 180 here. I'm basically plotting for each and every degree. I am plotting my range profile. Range profile is pretty accurate, right? I am doing that range profile. I'm just converting to the heat map, right? So I'm basically putting rotating from 0 to 180, and I'm putting all the range profiles. I'm basically converting that to the heat map. If there are 5 targets, I basically get the image like this, right? So my objective is to find the center point of this one, right? If I know the center point of this one, then that will be the angle, right? So it's very easy, right? You know YOLO already. You basically run through the YOLO these things. Then you basically get the nice bounding box. You basically extract the center. You basically tell the angle of arrival. Very simple concept. Okay. Then we did another thing. For example, all these are humans. Then there are also drones also are there. There are also cars are there. If there is a car, for example, if there is a car, you will get a huge reflection. If there is a drone, you will get a small reflection. We used those features also to be able to tell, okay, whether this is a drone or whether this is a car or whether this is basically human. Classification also we have done with just it is very hard to classify with radar because you basically do not get the image, but we accurately classify it, right? This is working very well in a perfect, very neat environment setting. We have not used any other noises and all. Obviously, when you have the noises or any other interferences, it will definitely not work. Okay, there is a fundamental limitation on this, but this will work on the drone. On the drone, it will work perfectly because you do not have any other reflections. We have done the measurements in a clean and nice parking area in a very free space so that we got a nice measurements. Of course, we did not get the measurements for the first time. After several iterations, we succeeded to be able to get a nice images. Of course, if it works for the first time, then there's something wrong. If you go and if you measure something, if it works for the first time, then there's seriously something wrong. Okay, then the classification works very well for UAVs, so especially cars and all, it is pretty accurate. For humans, we have a large number of instances, so that's the reason we have some sort of misclassification for the UAV as well as humans, because those sizes are very small, the reflection is very small. So, for example, a drone located nearby the radar as compared to human far, when looking at the image, it looks almost similar. Because drone located very small distance, it basically reflects the small amount of energy. On the other hand, human located very far will reflect a small amount of energy. When you look on these images, it looks more or less very close. So that's the reason we see some sort of misclassifications here for the UAV as well as human. On the other hand, car is pretty much a big object. You basically get the much higher reflection. So basically, overall, this angle of arrival estimation is pretty accurate. There's no doubt about it, but you have to rotate all the time. The rotor also, we bought very power efficient rotor. It basically runs with the AA batteries, right? You are free to take the whole setup anywhere, wherever you want. You can also put on the drone. It's very lightweight too, right? So the results are pretty accurate. I'm not getting into each and every minute details of that one, but that is the work we have done where we can basically work on the fundamental limitations of the angle of arrival, but doing some extra work such as the rotation, right? So those are the things about the radar. But when somebody is working with the radar, there are many things can be done. For example, not only radar, but GPS or any camera or LiDAR or spoofing is the major thing now. If somebody is able to do the same level of, if somebody is able to achieve the same level of performance in a neat data set with a spoof data set, then that is a big challenge. That is equally applicable to the radar as well. Any questions? Yeah, that is basically not telling any of these. The percentage is not matching closer to any of the three targets.
It's good to have
Yeah.
off diagonal elements
Yeah.
zeros.
Yeah. But that is not giving. That's not matching to any of the three.
And this respiratory thing you have told.
Yeah.
How does it work, sir? Are you measuring the movement of chest or
Chest? Chest
okay.
as well. Chest only. That is also under review. That is also very good. Radar based, the advantage of that thing is that you do not have to put any contact. The respiratory rate is pretty accurate because it is very nicely capturing.
You need to stay still while measuring.
Yeah, for a couple of seconds.
Yeah. Okay.
So what we have done is basically we have automated. You do not have to. Somebody doesn't have to come and sit in front of the radar, but we have mounted the radar on top of the camera. Camera basically finds the face, then basically it tilts the radar, then that basically points towards the chest. That's the work we have done. It's completely automated. Hope you got some basics, some things out of radar, how to do so that you feel like you are familiar with radar now. So before going out, if any questions, then the final slide is basically I'm going to get on. So we have a lot of, I basically recruit a lot of bachelor students, mostly from IITs and NITs, but in exceptional cases, we do consider from, for example, if someone is seriously interested in doing bachelor thesis or master thesis from normal, apart from IIT pool or NIT pool or Central University's pool, or we do consider if someone is really have a very good track record and really interested, we do consider taking for doing the thesis with us. Right? So you can look into these vacant positions. We have all the time, all the way up to 2024. If somebody is interested, we can do collaboratively also with the IIT. Okay, we are located here, very nice place in Grimsburg, very close by the sea. Very nice place during summers. Okay, yeah. If you have any questions, I can still take. Okay, you are free to drop an email also if somebody wants to work, or also we can take offline also, online also later.
Detailed background on radars. So it's a nice introduction for this field. Yeah.